Okay, we've got another microwave. And suppose you want to move this 500 Newton microwave across a level floor by pulling it upward on the rope at an angle of 30 degrees above the horizontal. How hard must you pull the rope to keep it moving with constant velocity if the coefficient of kinetic friction is 0.4? So let's make sure that we draw a picture so that we know exactly what is going on here. The microwave sits on the floor, and someone comes over and pulls it with a rope. And that rope makes an angle we can call theta, and in this particular example, that theta is 30 degrees. There's a force of gravity that acts on the microwave, which is 500 newtons. Force of gravity is mass times g, and that's equal to 500 newtons. There's also a normal force, which acts upward from the ground, normal force. And there's also apparently some frictional force. Force of friction, and it should be kinetic or sliding friction. So those are the four forces that we have. This is called the applied force. And now we're going to need to figure out what to do here. There is a lot going on, so let's draw a simplified diagram, simplified free body diagram. We've got our picture, but let's do the free body diagram. So this dot will represent the microwave. There is 500 newtons pointing down, or I'll just call that force of gravity equal to mg, and we'll plug in the numbers later if we need to. Normal force pointing up, and force of kinetic friction pointing in this direction. The applied force points at an angle, and right away that suggests that we're going to need to find the components of that force so that we can either deal with the x direction or the y direction, but not try to do both at the same time. So if this is the applied force, then what I would suggest we do is throw in some dashed lines so that we can figure out what the components of that force is. Those components I'm going to draw in a different color. I'll put those in green, and then we're going to neglect the blue arrow that I've already drawn. This arrow here, that will represent the applied force in the y direction. So not the full amount, but just the y component of that vector. This will represent the x component of the applied force. So when it comes time to use Newton's law, Newton's second law, we will only deal with the green and red arrows, not with the blue arrows. Okay, we've got the free body diagram, we've got our picture. What are the possible concepts that we're going to need? We're dealing with forces, which means almost certainly we're going to need to use Newton's laws, Newton's second law. And we're going to need to use what we know about friction, specifically the model of kinetic friction or sliding friction. The relevant equations that we might need: Newton's second law, the net force is equal to mass of the object times acceleration. And the kinetic friction, according to the model, is that it has a magnitude given by the coefficient of kinetic friction times the normal force. So let's see if we can get to the answer quickly. It'll turn out that we actually need to do a little bit more work than you might first expect. Since we want to learn something about the frictional force which points horizontally, that suggests that we'll use the horizontal component of Newton's second law. In other words, Newton's second law in the x direction. The net force in the x direction, well, it's the applied force, its x component, F applied x, minus the frictional force. That's equal to the mass times the acceleration in the x direction. And there's a lot going on here, but it should get a little bit simple. And I say that because there's some information that we learn. The object is going to be moving with constant velocity. That tells us the acceleration is 0. So the whole right-hand side of that equation is 0. The frictional force obeys this model, at least we'll assume that the model works. So there's mu k times the normal force. And lastly, let's just use our trigonometry now to realize that the x component of the applied force should be the hypotenuse of that right triangle times the cosine of theta, because that's the adjacent side of that triangle. So when we simplify things here, it seems like the applied force times cosine of theta, if we take this term to the other side, will be equal to mu k times the normal force. Or applied force is equal to mu k normal force divided by cosine of theta. And you might think that we're basically done because we know what mu k is, we know what theta is. So if we can plug in the value for normal force, we'll be all set. But we have to be very careful. We have to be very careful because in general, the normal force is not equal to the gravitational force on the block, on the microwave, I should say. Why is that? If you look at the diagram that we drew, the free body diagram, there are three vertical forces. There's a normal force pointing up, there's also the y component of the applied force pointing up, and there's the force of gravity. The fact that there's this applied force changes the value of the normal force from what it would be if that wasn't being applied. Another way to say it is that the floor doesn't have to push as hard to keep the microwave upright. Let's see exactly what we mean by applying Newton's second law in the y direction. The net force in the y direction is equal to the normal force, the thing that we need, plus the applied force in the y direction, minus the force of gravity, because that's how we account for the direction, minus mg. That is all equal to the mass times the acceleration in the y direction. But as we just got done saying, there is no acceleration because the object is at constant velocity, and therefore the entire right-hand side of this equation is equal to 0. Let's now put in what simplifications we can, recognizing that the applied force in the y direction is equal to the applied force magnitude times the sine of theta, as it must be. We're talking about this vector is the same as this vector. And so, when we apply that, we learn that the normal force is equal to mg minus the applied force in the y direction, which is mg minus the applied force times the sine of theta. So this is why this problem is much more complicated. The normal force contains in it the applied force, which is the thing that we're trying to solve. So what we need to do is insert this result into our previous result for the applied force. I'll start it out so you can see where it goes. The applied force is apparently equal to mu k times the normal force, which we just found, mg, minus the applied force times sine of theta. Divide that all by cosine of theta. You'll have to do a little bit of algebra here, but when you get done doing that algebra, you should be able to solve for the applied force. And I'll leave that to you to work it out. It should work out to be mu k times mg divided by 1 plus mu k times the tangent of theta. When you plug in the values given in this problem, mg is 500 newtons, theta is 30 degrees, and mu k is 0.4, you should find that the applied force is about 188 newtons.